Okay, we're going to talk about conic sections now. This is the third section. So, our learning goal, we're going to recognize four basic types: circle, ellipse, parabola, and hyperbola. Hopefully you'll also be able to recognize, graph, and write equations of parabolas, vertex centered at the origin. And hopefully you'll be able to recognize, graph, and write equations of ellipses and hyperbolas. So first off, let's start with what a conic section is. Conic section is you take two cones and tip them upside down to each other like this. If you slice a plane through one of the cones horizontally, you'll get a circle. If you go at an angle, you'll get an ellipse. If you go at a larger angle so that the part of the circle, I guess, or part of the ellipse is cut off, then you have a parabola. And if you go straight up or straight down vertical, you'll have a hyperbola. All right. Then you can also get a point if you go right through this location here. If you take a plane and go at an angle, you can get a line. You can get intersecting lines as well, or the plane that goes straight up and straight down through the middle. Okay. There are different ways to look at these conics. The Greeks used the method I just showed you to look at conic sections. This is the algebra way of looking at conic sections. They're going to have this form. We'll talk about this. We'll be able to take this and put it into standard form by completing the square. We'll do that later. And also the third approach is to look at a space called a locus, which is defined as a set of points that satisfy a parabola or hyperbola. So let's take a look at that approach. Here's our first equation, which is the equation of a circle. A circle is defined as all the points that are equal distant from a fixed point, hk. So here's an equation for a circle that's centered at hk. It has a radius r. Now, you don't have to memorize these equations. This one's easy enough where you use it enough you might memorize it, but I have all these written down for you on the formula sheet. It's going to be hard for me to put this up in class, so you might want to print this off. But we have parabolas, ellipses, hyperbolas here. I don't have the equation of circle on there because it's actually one specific case of an ellipse where a and b are equal to each other. So if a and b are equal, let's say they're both 1, then you'd have a circle with a radius of 1. Okay? If a and b are both 4, if a is 2 and b is 2, then you can multiply through by 4 and you'd have a circle with a radius of 2. Okay? If a and b are 3, then you have a circle with a radius of 3, and so on. So let's look at a parabola then. Okay, here's an equation of a parabola you guys are used to. You used to see in y equals ax squared plus bx plus c. Okay, but the definition of a parabola is something you might not be used to. The definition of a parabola is all the points that are equal distant from the focus and this line called the directrix. So let's take a look at that real quick. A parabola is defined as all these points right here, like this point, is equal distant from the focus as it is the directrix. Okay, now, which obviously makes then even the vertex. The vertex is equal distant from the focus as the directrix. So that tells you how to set these lines up. The directrix is a line that's going to be perpendicular to the line that goes through the focus in the vertex. And it's going to be equal distant away from the vertex as the focus. That's going to be important that you understand that, because that's how we're going to set up our equations. Vertex at the origin. I just give you the equations on my formula sheet are centered at hk. All right, that way we can shift these around. We don't have to have them centered at the origin. So you'll notice on my formula sheet for ellipses and parabolas that mine has the x minus h, y minus k. Technically that's tomorrow's lesson, that's 4-4. But I like to just give that equation right away, because obviously it's centered at the origin. Then you can just plug in h and k is 0, and you get this equation. Okay, this is the equation for a parabola with a vertical axis, one that opens up or down like this. As you remember, if you have y equals x squared, you know that's a parabola centered at the origin. And then obviously, if I have a horizontal axis, it would look like this. Okay, let's do a quick example then of the equation of a parabola with vertex at the origin. All right, so this is a parabola, vertex at the origin. and focus at 2, 0. So we're going to graph this real quick. Focus is at 2, 0, which is right here. And it's the vertex is at the origin. So if I graph this parabola, it's going to look something like this. And I can draw the directrix in as well. The directrix would be 2 units back, and it would be this vertical line. Okay? So this parabola is defined as all the points that, like this point, must be the same distance from the focus as it is from the directrix. Those distances must be the same. But I want to write an equation for this. So I'm going to go to my formula sheet. It's a parabola. It opens right or left, so I'm going to take this equation right here. And it's centered at the origin, so I can plug in 0 for k and 0 for h. And then p, so let's use x here. P is the distance away from the vertex, the focus. So p is this distance here, 2, or this distance here. It's always the same. So p is 2. So this equation becomes y squared equals 8x. And you can leave it like this, that's fine. I know this technically isn't a function because it doesn't pass the vertical line test, but it is an equation of a parabola, of a parabola that opens sideways, left to right. Let's talk about some application of parabolas. Parabolas occur in a wide variety of applications. Some, like reflectors, as you guys know, for antennas collecting electromagnetic radiation. The nice thing about a parabola is it's got a focus. And one of the properties of that is that when light waves, in this case, if it's like a satellite dish, when electromagnetic waves, which are just light waves, come in, they all reflect at an angle, no matter where they hit, they all go to the focus. So if a light wave comes in here, everything gets reflected to the focus. So this spot right here is going to obviously pick up a lot. It's going to be an amplified signal. So that's obviously one helpful use of focus. Obviously in telescopes as well, for focusing light rays to a single image to a single point. For sound, if you want to amplify sound, like in the University of Chicago, the Museum of Science and Industry in Chicago, they have a whispering gallery where it's a room with 2 parabolas on each side. And what happens is you stand at one vertex and you have someone go to the other focus, someone go to the other focus of the other parabola, and you guys can whisper across a 40-foot room and hear each other like you're standing right next to each other. It's kind of cool. Whenever you throw a ball, the ball's getting pulled down by gravity, in which case it's going to have the shape of a parabola. Any falling objects has the shape of a parabola, given some horizontal speed. Another example is a parabolic lens that would then focus light to a specific point, like your contacts, so you can get the image where it needs to be on your eye. So all kinds of applications that are helpful for us. Also, planets traveling in orbits. If you have we'll go over this more in a second, but here's the sun. If a comet comes into our solar system and it's traveling around, if it has too slow of a speed, then it'll go into orbit, where the sun will be one focus of the ellipse. Okay? If it's traveling fast enough, just the right speed, then it'll actually be a parabola. It'll come in and it'll be affected by the gravity of the sun and it'll fly off, so it'll actually be a parabola. If it's going too fast, then it'll be a hyperbola. Okay? So those actually show up in astronomy as well. Also, a flashlight. If you have a parabolic mirror here and you put the flashlight at the focal point, then all the rays will go parallel, so you can keep the light going. It's not going to focus on one spot. The light will just keep going. Otherwise, you have a beam that spreads out, and as it goes out, you lose intensity of the light. All right, let's talk about ellipses then. An ellipse is a set of all points that the sum of distances from 2 fixed points is constant. So if you look at this right here, the definition of ellipse, as we're going to talk about it, is not from the conic section, but from the locus of points. So basically, this point here, for example, is equal distant from, if you add up the distances from both focal points, that distance is always constant around. So this point right here, if you add up the distances from both focal points, it's constant, that number that you get when you add these up. So if this is 3 and 5, then this would be like 2 and 6 or whatever. It always add up to 8, no matter where you are. some vocab. This is the major axis, this is the minor axis. This is obviously the center. These two are we're going to call the vertices, which are going to be important for understanding the formula sheet, because when we look at ellipses, we have tons of information. I'm going to give you not only an equation, but how to find the foci, the vertices, and then you need to know what those are, obviously, in order to find them. So let's try an example then. Let's find the standard form equation of an ellipse here. This ellipse has a major axis that goes horizontal. So when you look at the formula sheet, you're going to look at this and you're going to say, okay, well, here's my equations I can use. Okay, so this one here has a focal axis of y equals k. That's a horizontal line. So this one goes horizontal and this one goes vertical. So let's look back at ours. This one goes horizontal. So we want to use the first one. So let me grab that. You can do it. So this distance right here is A, which is 3 in this case. So I know A is 3. This distance is B, right here, which it looks like an irrational number. It looks like it might be the square root of 2. It's centered at the origin, so h and k are 0, 0. So my equation becomes x squared over 9 plus y squared over b squared equals 1. So the only thing I've left to find is b. I'm going to use this information, then when I look back at the formula, I'm going to use the foci. So I know the foci are at h plus or minus ck. Let me copy that over. Like I said, you'll be able to do the same thing on a quiz or a test. So these are where the foci are at, which I know are here. They give me the foci. So basically, I know it's centered. I know h is 0 because it's centered at the origin. So I have plus or minus c comma 0 for my foci when it's centered at the origin, because h and k are 0, 0. So that's plus or minus 2 comma 0. So I know my c is 2. Okay, so I know a is 3, I know c is 2. Now what I can do is look at the Pythagorean relation right here, a squared equals b squared plus c squared, and use that to find b. A squared equals b squared plus c squared. So I know a is 3, so that gives me 9. I know c is 2, so that gives me 4. So subtract and you get the square root of 5. So I know b is equal to the square root of 5, which then would make the equation 25 right here. So here's my equation. And it makes sense because the square root of 5, I'm sorry, this would be 5. It makes sense because the square root of 5 is about 2.23, which is right here. So it makes sense that b is the length of the semi-minor axis. But I couldn't find the length from the graph, so I had to use the Pythagorean. I had to use information about foci and the Pythagorean relation in order to find the coordinates for it. Or to find this length right here to plug into b. Now, you can always check this in your calculator to make sure you got the right answer. So what you're going to do is go to apps. Go to and you click on conics. I don't have it on here, unfortunately. I'll put it on this calculator later and show you on the homework help video maybe. But if you click on conics, then you can choose between circle, ellipse, hyperbola, and parabola. And you want to click ellipse for this one. And it's a horizontal one. So then it asks for A, which we found A was 3. It asks for B, which we knew was the square root of 5. And then it asks for the center, which is at 0, 0. If you hit that, it'll graph it. And you should get this same graph. That way you can check out if this equation works. There's other ways I'll show you later to check this equation. Is that equation of ellipse? We'll have to talk about that later.